Hi, it's Kate, and this is a little short video for Math 23B talking about the penultimate example in Thursday's lecture of change of variable. And the goal of this problem was to integrate a particular function over this region in the original space by using this change of variable that was given to us. And everyone feels generally pretty okay with finding the determinant of the Jacobian, using that as the stretching and scaling factor, composing the original function with the new parameterization. And then the real issue is, how do we represent this triangle in the original space with this rectangle in the parameter space? How and why does that work? And so I wanted to take a few minutes to clarify that, just to make sure that if anyone has any lingering questions, they're 100% clear on this after watching the video. Let's take a look. Most of us don't disagree that u equals x plus y varies from 0 down here to 2 over here over this region. And in fact, if we take a look at that inequality and what it represents, that u is greater than 0 and less than 2, what region do we have in the original space? Here I've represented it just as u is greater than or equal to 0, less than or equal to 2. You guys have already done the problem set problem where you know that equality on those endpoints is not an issue with computing this actual integral because it's a set of volume 0, etc. But what you have when you look at this space that where u varies from 0 to 2, we're looking at this infinite strip that lies on the plane that's below the line x plus y equals 2, but above the line x plus y equals 0. So how do we take this strip right here and also combine it with an inequality for v that will leave us with just this triangle that we care about? Now let's take a look at v. V given to us is looking at the two components of a point in the plane, the x component and the y component, and v is equal to the proportion that the y component of a point is to the sum of the x and y components of that point. So the fraction that the y component is to the sum of both the x and y component. When we look at this particular line right here, y equals x, right? Along this line, what's happening is that y is exactly 50% of the sum of the x and y component. And then when we look at the area above that, that is where y is more than 50%, but less than or equal to 100% of the sum of the components. Now all along the y-axis, x is 0, so that means that the y component is 100% of the sum of the x and y components because the x component is 0. And furthermore, when we say that, okay, v should be greater than 0.5, that means that y is going to be more than 50% of the sum of the x and y components, which is the entire area of the plane that is north of y equals x. And I should be clear that that is in the first quadrant, because the second we move over into the second quadrant in the Cartesian plane, where actually the y component is going to be more than 100% of the sum total of the x component and y component, because the x component is negative. So we have to realize that when we're describing parameter bounds, it's these two inequalities taken together that describe our region. And so when we take a look at the region in the plane where both u is greater than or equal to 0 and less than or equal to 2, and v is greater than or equal to 1/2 and less than or equal to 1, that means y is between 50% and 100% of the sum total of the x and y components. We're looking at both the red shaded region for the v inequality and the blue shaded region for the u inequality, and that's leaving us with exactly what we desire. Combined, we get our purple triangle that we have been hankering for. I've tried to color code it accordingly. It's not exactly the best artistic representation, but I will say that v is equal to 1/2 all along the line y equals x, that v is equal to 1 all along the y-axis, u is also equal to 0 right here, but sort of out here, so this doesn't have a corresponding boundary in the triangle in the original space. But this blue side, where u is equal to 2, is this blue side over here. So that might give you a little bit better of a visualization of what's going on. But I think approaching it this way is much more helpful. So the important thing to realize is that only one, as I was trying to pretty ungracefully explain in lecture, Since both of the inequalities have to hold at the same time, you really only need to account for certain boundaries one time. So for instance, if you're looking at something like in the small group problem where you have a hemisphere that's been sliced. Oh dear, that was gross. All right, there we go. This is why we don't draw anything live in these videos, people. But anyway, this is a hemisphere of radius big R. And so that means that the white boundary, sort of the entire northern hemisphere, can be described using this cylindrical coordinate equation. And let's say that this hemisphere is sliced at height h. Well, how do we use our new coordinate system, r, theta, and z, to describe exactly what's happening here? Now, a lot of people want to just immediately approach this similar to how we were approaching it using rectangular coordinates, where we say, okay, let's walk in a z-wardly direction sort of through the bottom of this sphere. When we enter the hemisphere, we go through z equals 0, and as we leave, we're going through z equals h, and those are the bounds for z, and then r goes from 0 to big R, and then theta goes from 0 to 2 pi, and that's it. So that's what they think the bounds are for this. But that would actually be incorrect, because these bounds right here, they actually describe a cylinder. I could draw it in here. That looks like this, right? It's not taking into account the fact that there are these curved edges on the outside here, because if you travel in a z-wardly direction, these bounds, 0 to big H, are only true if you manage to go through the region sort of in the middle of it. If you're out by the edge, you will go through z equals 0, but you'll exit through the hemisphere, which is r squared plus z squared equals big R. So these are incorrect bounds for this particular lime green hemispherical sliced thing. All right, what do you do instead? Well, the key here is that you need to introduce the fact that there is this r is changing. Distance from the z-axis is changing along here depending on what value of z you are at. And so you want to include that boundary condition in one of the inequalities. So what does that mean? Say I'm hanging out on the z-axis and I start marching out. I'm keeping z constant. I'm keeping theta constant. I'm marching outwards along increasing r. I've started at r equals 0 and I exit out here, right? And this surface of the hemisphere is described by r equals square root of big R squared minus z squared. That is just the equation of the hemisphere solved for r, knowing that r can only be positive. And this is true no matter where I start along the z-axis within this region. The coordinate will always start at 0, and you will always exit the region out of some point that's described by this. And so this inequality, the fact that we can say this about r, has taken into account that this boundary changes depending on z. So we don't need to accommodate that again twice when we then compute the bounds for z. Z, we can just say, okay, z is going from 0 to h now, and theta is going from 0 to 2 pi. So in a way, this approach is similar. I think the big hang up is that it's difficult to realize that you don't need to incorporate all of the boundaries in each of the parameters, because some of the parameters just won't be able to include everything at the same time. The key is that you are correctly describing the region when you take all of these inequalities into account. Once you have r less than this function of z, you know that distance from the z-axis will be changing as you're moving northward through this hemisphere, and that's great. You only need to incorporate that in one of the variables for it to hold correctly, regardless of if you have constants over here, because the key is that all three of these have to hold at the same time to describe your solid. When all three of these hold, you end up with the light blue cylinder, which is not the region that we're looking at. Similar over here, like I said, what I tried to say in lecture, but I don't think came across very clearly. You need to use each of these inequalities together. And no, none of the inequalities, like you going from 0 to 2, won't be able to describe this purple triangle in its entirety, right? It actually describes this entire strip. And V going from 1/2 to 1 doesn't describe the purple triangle either. It actually describes the infinite region that's above this y equals x in the first quadrant. But what's interesting is that together they correctly describe the purple triangle, and that's what we're looking for. So I hope that this discussion of parameterization and trying to find the bounds of your region of integration in different coordinate systems has been helpful to you. This in particular certainly shows up on your problem set for this week, and I wouldn't be surprised to see something like it show up in a quiz question. So if you have any questions at all, please don't hesitate to email or ask in office hours. Thanks so much, guys. Enjoy.